In this video, we begin our study of gases, and we'll look at the kinetic molecular theory in the next few videos. What we're going to do with gases is look really at their, spend some time on their mechanical properties. And you might ask the question, why do we care about the mechanical properties of gases in a chemistry course? Wouldn't that be better suited to a physics course or an engineering course? Fluid dynamics is studied in engineering and mechanical properties in physics. But there are a couple of reasons that we do this. First off, gases are very important, and the measurement of gas properties turns out to be an essential element for lots of chemistry laboratories. In our laboratory, we regularly make gas measurements, and we use the ideal gas law for measurements of properties of substances that we're working with. But the more important reason is that the gas laws themselves were used to gain insight into the structure of matter and led to the understanding of the atomic and molecular models for matter and the discreteness of matter. And when we get to the kinetic molecular theory, we'll see how this ties in. So in the first video, we're going to go over basic discussion of the states of matter and gas pressure and how it's measured. And then we'll look at the gas laws and how we express them mathematically and their experimental foundations. When we think about states of matter, we think of solids, liquids, and gases. We don't necessarily worry about plasma or other sorts of states. So we worry about gases and liquids and solids in chemistry. And gases are different from liquids and solids in the following ways. Gases tend to have a very large compressibility. That is, if you squeeze a gas, its volume decreases substantially. And that's not the case for solids and liquids. Gases also have a very large coefficient of thermal expansion. That is, that when you heat a gas, its volume increases significantly. And it's much larger than for solids and liquids. It can be up to a couple of orders of magnitude more. Gases have very low viscosities. That is, they have a very small resistance to flow. They flow very freely. We would say they diffuse very rapidly, and we'll see that later on with some diffusion laws. They tend to have very low densities compared to solids and liquids. And we'll find out that their densities are related to their atomic masses. That is, their combining ratios in chemical reactions. That's one of the key ways that we tie together gases with some of our molar models and theories. And finally, gases tend to form solutions in any proportions. That is, they are readily miscible within each other, which is not the case for liquids and for solids. We'll see some of that in chapter 12, some explanation for that. Gases can phase separate, but they generally don't near room temperature and under normal conditions near sea level. So one of the first things we need is to understand gas pressure and how it is measured. Pressure of a gas is a derived unit. It's the force per unit area, and of course force and area are also derived units. Pressure is the force per unit area, and atmospheric pressure arises from the force exerted by the gases in the atmosphere on the Earth's surface. So gravitational force pulls the gases down, and that creates pressure. Atmospheric pressure decreases with increasing altitude at lower levels. We'll see later on, we'll see a picture where we see some unusual inversions. But in the troposphere where we live, atmospheric pressure decreases with increasing altitude. Here's a simple illustration of the effect of atmospheric pressure. You have an empty canister, the paint thinner can, and if you seal that up and then use a vacuum pump to suck all the air out from the inside, there's no counterbalancing force, and while the metal itself has some structural integrity, the atmospheric pressure is enough to collapse the canister. So it's enough to break down the structural integrity of the metal. The ways we measure pressure are a couple of ways. We have barometers and we have manometers. Now, a barometer is used to measure the pressure in the local environment, that is, the atmospheric pressure. And the way this is measured very often is with a mercury barometer. Mercury is not used as much anymore because mercury is a neurotoxin. Mercury is a liquid at room temperature and it vaporizes. There's a small vapor pressure above that. And mercury atoms that come off, if you breathe them in, they're neutral and they can pass the blood-brain barrier and they're not good for your health. And so now we have electronic barometers to measure pressure that way. But this shows us the basic definitions of how we measure pressure and the units that we use. And what you see is the pressure exerted by the atmosphere due to the weight of the atmospheric gases is equal to a column of mercury that's 760 millimeters high. So this is at sea level. At sea level, the pressure for all the atmospheric gases going up to, up through the thermosphere that press down onto the Earth's surface apply as much force per unit area as does a 760 millimeter tall column of liquid mercury. Mercury is chosen for measurements because it's a very dense liquid, and so a 1 meter tall column then is a little bit shorter than 1 meter tall column is easily accessible and measurable in a laboratory. So this is how we measure atmospheric pressures with a barometer. In laboratory, inside a reaction vessel, like this evacuated flask here, we use a manometer. And there's two types of manometers. This is a closed-end manometer. And we would use this for a system that is under vacuum and then evolves gases over time. And for example, in our laboratory, if you can take a redox reaction like we talked about earlier. You can take your aluminum nanoparticles, your aluminum metal, react it with water, and it will release hydrogen gas. So we can do this under vacuum, and as it releases the hydrogen gas, then that gas will create pressure. And if we use a closed-end manometer where both sides are evacuated, then as the gas is released, it will push down on the column of mercury. Then the height differential there, delta H, will tell you what pressure you have inside your evacuated flask. So this would be something where you're starting with zero pressure, you release your hydrogen gas, and if you produce, for example, 10 torr of gas or 10 millimeters of mercury, then you would see a displacement of 10 millimeters on your closed-end manometer. So that delta H value there for the closed-end system tells you the absolute pressure inside your evacuated flask. Now, an open-end manometer is for reactions that are carried out near atmospheric pressure. So in this case, the side away from your reaction flask or your reaction volume is open to the atmosphere. So you have atmospheric pressure on that side of the column of mercury. Inside your reaction vessel, this will create pressure. Now, if you end up removing gas from your vessel, then delta H would be on the left-hand side, where the column closest to your reaction vessel is higher up, and that delta H value would give you your pressure differential. And so in this example here, the pressure of the gas inside the container is the atmospheric pressure minus delta H, that is that column height in millimeters of mercury. So if it was 10 millimeters high, then that would be a 10 millimeters of mercury or 10 torr difference. Now on the other side, this is a case where you're releasing gases and the pressure is higher than the atmospheric pressure. And so the pressure of the gas is the pressure of the atmosphere plus delta H. Here now are common units of pressure that we will use. So the first four and the last one are very commonly used. Pounds per square inch or PSI is not used very commonly anymore. You will see that for some American products, but most engineering and science labs will use pascals, atmospheres, millimeters of mercury or torr, or bar. So millimeters of mercury and torr are equal to one another. Torr is a callback to Torricelli, who did early work on properties of gases. So 1 atmosphere is a defined quantity, so it has as many significant figures as you need, as well as 760 millimeters of mercury or 760 torr being related to 1 atmosphere. Your measured value will have its measured number of significant figures. Now, these were commonly used many years ago, but now the Pascal is the preferred unit for pressure. We'll use all of these units, particularly the first four, and sometimes we will use bar, but you'll be given appropriate constants to do these conversions. So this table here is worthwhile to print out and have available to you when you're doing your practice problems, and then you can get comfortable with these units. And you can see the relationship, for example, 1 atmosphere equals 1.01325 times 10 to the 5th pascals, or 101.325 kilopascals. That's equal to 1.01325 bar. And so you can see that 1 bar equals 100 kilopascals. So bar and kilopascals are related, just like torr, millimeters, and atmospheres are related. Next, we're going to look at what are termed gas laws. The gas laws are mathematical relations that tie together the key properties of gases. And the key properties, we alluded to those much earlier, are pressure, temperature, volume, and then the amount of gas. And the pressure, temperature, and volume, of course, have to do with the thermal expansion coefficient and the compressibility coefficient of the gases. We'll look at the basic relations, and then ultimately we're going to lead into something termed the ideal gas law. So the ideal gas law, or ideal gas equation, is a relationship that is observed for most gases, particularly near atmospheric pressure. So in common laboratory environments, the ideal gas law works quite well to describe the properties of gases. Now, it turns out it doesn't exactly describe it. They're much more complicated equations, but it's always nice to have an easy equation that you can write on the back of an envelope and do a quick calculation yourself in your head to estimate properties of materials. Now, it turns out that there are no truly ideal gases, but near atmospheric temperature and pressure, you find that it is a very good descriptor for most gases. The first relation we're going to look at is what's termed Boyle's law. Now, you don't need to memorize Boyle's, the name Boyle's, Charles, Gay-Lussac, Avogadro, and so forth. We're not going to ask for any history. But what we are interested in is that you understand the relationship between the various properties. And the Boyle's law relation is between volume and pressure of gas. Without looking at the math first, the simple relationship is if you squeeze a gas, its volume goes down. If if you take the pressure off a gas, it'll expand. Right? And so the relationship is, as the pressure goes up, the volume goes down. As the pressure goes down, the volume goes up. So I think that is an intuitive relation that you would probably maybe even have experienced before. If you haven't done this in lab, it's something where if you do basic mechanical work around your house or in a shop, you'll have seen this. And so here are experimental data for a particular measurement, and then these are written on graphs. The upper right-hand graph shows volume versus pressure, and you can see as the pressure goes up, the volume goes down. It's a simple inverse relation. And so if I plot volume versus 1 over pressure, it is a linear relation. And what that tells us then is volume divided by pressure, or volume multiplied by pressure, is a constant, because volume is proportional to 1 over the pressure. And so P times V is a constant. This only holds for a constant amount of gas at a fixed temperature, but the volume versus 1 over P is linear, so PV is a constant. Pressure goes up, volume goes down. Our next relation is it's termed Charles' law, and that's the relationship between the volume and the temperature of a gas. And this is another one you may have seen just around your house. As you heat up a gas, it expands. So if you have a balloon, you go to the store and you get a balloon, maybe a birthday balloon or an anniversary or celebration balloon, and if you have it floating around your house and the temperature drops in the house, you'll see that the volume of the balloon will go down. Okay? The volume will shrink because the temperature has decreased. And so here you can see that on a graph in the lower right-hand corner. Volume versus temperature is linear. As the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. This brings us to an important point, and we'll see this when we do in our mechanics videos for this chapter. We're going to need to use an absolute zero temperature scale. And it turns out this is an easy way to measure the lowest attainable thermal temperature. If you take a gas and you measure its volume-temperature relationship, you can linearly extrapolate that gas property all the way back to the lowest volume you could have, which would be zero volume. And you'll see that this extrapolates back pretty well. If you do an experiment in life, you do it well, you'll find out that the lowest temperature is minus 273 Celsius. And so this is how the absolute temperature scale was developed. And the absolute temperature scale starts off with the lowest thermodynamic temperature of 0, and this is termed Kelvin. So from now on in this course, it is recommended that you use Kelvin scale for all your calculations. You'll find out that you can do some shortcuts once in a while and not have to. If you're doing a difference temperature measurement, you can stay with a Celsius scale. But as a simple rule of thumb, to avoid problems and errors, switch to the Kelvin scale throughout this course. The thing that's really quite cool, quite nice, is there's a relationship between these gas laws and the behavior of engines and machines and thermodynamics that we'll come across in Chapter 6. So we'll see that the constants that come out from the slopes of these graphs are also related to the amount of heat released in solution chemical reactions. It's quite amazing. So the key take home here is, whereas in the Boyle's law, as the pressure went up, the volume went down, here as the temperature goes up, the volume goes up. Therefore, volume is directly proportional to temperature. And so the volume divided by the temperature now is a constant. And this requires that the pressure is fixed and the amount of gas is fixed. And in that case, then the volume and the temperature have this V over T relationship. So V1 over T1 is equal to a constant. As you cool a gas, its volume goes down. As you heat a gas, its volume goes up. The next law that's not really addressed in your text as much is Gay-Lussac's law, but this is worth thinking about. Sometimes this is called Amonton's law, though Amonton was not actually able to make sufficiently precise measurements. He was one of the first to try and measure absolute zero, and this is the relationship between pressure and temperature. And the simple law is this: heat a gas and the pressure goes up. That is with a fixed volume. And you can prove this to yourself, but you shouldn't try this at home. Throw a spray paint can in a bonfire, and what do you think happens? Well, we all know what happens. The pressure goes up until the canister ruptures, and you get an explosion and a fireball. So don't do that. But that is what Gay-Lussac's law is. Under fixed volume and amount of gas, as you heat it up, the pressure goes up. So now pressure over temperature equals a constant, or P1 over T1 equals P2 over T2. The final relation we'll look at is the relation between volume and the amount of gas. This is sometimes called Avogadro's law. And very simply put, the more material you have, the more gas you have. And that probably is somewhat intuitive to you. You can prove this to yourself if you take solid carbon dioxide, which has very small volume, and carbon dioxide is a gas or a solid at room temperature. It doesn't have a stable liquid phase at 1 atmosphere. So dry ice, as it's often termed, will go directly to a gas, and if you double the amount of carbon dioxide, you double the volume of gas that's produced when it undergoes this sublimation process. We'll discuss sublimation in chapter 12, but for here, for our purposes, as N goes up, V goes up. And what we find is an interesting relation. But first we have a definition of what we call STP. This is standard temperature and pressure. And that specifies pressure of 1 atmosphere and a temperature of 0 Celsius, which is 273 Kelvin. So under standard temperature and pressure, 1 mole of gas occupies approximately 22.4 liters of volume. And of course, if you had a half a mole, your volume would be half of that amount. So that leads us to what we call the molar volume of a gas at STP. The molar volume of a gas at STP is 22.4 liters. And this starts to take us into the molar relationships, which we really learned in chapter 2. So if you take hydrogen as a gas that exists as H2, it has a molar mass of 2 grams per mole. So 2 grams of hydrogen gas at STP will occupy 22.4 liters. The chemical combining ratio for nitrogen is different. And of course, N2 gas is the elemental form of nitrogen, and that has a molar mass of 28. So that tells us 28 grams of nitrogen occupies a volume of 22.4 liters. So now we start to see the relationship between gas properties and chemical combining ratios. So this ties together two things that really may seem to be unrelated or intuitively seem unrelated, but they are tied together. And this is why gas laws are important. And here's a picture of how this behaves. So we've got helium, nitrogen, and oxygen, 3 very different masses, 4 versus 28 versus 32 for helium, nitrogen, and oxygen. We talked about hydrogen a moment ago, but this is helium. So for hydrogen, it would be only 2 grams, right? And you can see the relationships that fall out here. In our next video, we'll tie all of these gas laws together into what we call the ideal gas equation.